Welcome once again. So, we shall continue our discussion on the homogeneous to heterogeneous transformation from lab to industrial journey. And in the last class, we have discussed about the basic concept of the heterogeneous catalyst system, and we have also tried to understand in a comparative way what is the basic advantage and disadvantage from homogeneous to heterogeneous. And also we learned that what are the very important and like a path breaking heterogeneous catalytic systems which are accepted in industries, and still it is used heavily. So, today mainly we will discuss about the first part. We will discuss about the mechanism, how does it work in heterogeneous catalyst, and then we will try to discuss that what are the strategies to make the homogeneous metallocene catalyst to heterogeneous catalyst for practical implications in industries. Okay. So, the concepts are similar as our last classes, okay, because we are continuing the discussion. So, here mainly we will be discussing the mechanism, okay, and the metallocene catalysts on support, how to do it. Okay. So, if you recall, in the last class we have discussed the important steps, that is the diffusion, because as we discussed, that is a surface phenomena, then physical adsorption, okay, and then will the chemical reaction, and then the last step is the desorption. Okay. These are the, and all you see that heterogeneous is a surface phenomena. So, the nature of the surface of the catalytic system plays a vital role in heterogeneous catalysis. Okay. One very classical example I want to give is a textbook example, but it is very important and very interesting to discuss. Like this, the classical reaction plus H2 plus O2 is H2O. As you know, this is thermodynamically favorable reactions theoretically, because the delta G0 is, any idea how much is yes, spontaneous minus 32 kilojoule per mole. Okay. However, the bond dissociations energy of the HH, okay, that is the bond dissociation energy, is very high, okay, and almost similar in H2 and O2. This is 412 kilojoule per mole, and this is 418 kilojoule per mole, is very much similar. So, if you keep H2 and O2 in a sealed glass container, you will see nothing happens, okay, there is no reaction at all, but theoretically this reaction is feasible, because you see the delta G0 is quite negative, minus 232 kilojoule per mole. But this reaction only happens, okay, in presence of the platinum gauge or platinum catalysts, okay, heterogeneous catalysts, platinum catalysts. Okay. So, and this is also one example of the heterogeneous catalytic system, heterogeneous catalysts. Here is a heterogeneous, this is very interesting system, okay, and how does it happen? This is activation energy is very high in this case, because you see the dissociation energy is quite high here, but in presence of the platinum it takes a different path. So, it actually first activate the small molecules like hydrogen or oxygen, and to make the platinum hydrogen, platinum hydride, and the O2 PT is PTO. So, is basically you see these are the activation steps. Okay. So, and then it undergoes through a low energy pathway to form H2O. Okay. So, this is a very classical example of heterogeneous catalyst system. Most of us, we are aware of that one because it is textbook chemistry. Okay. In the next one, I will try to discuss or try to give some highlight what are the basic steps of any heterogeneous system that is applicable for any kind of heterogeneous catalyst, whether it is a polymer supported, whether it is a silica supported, or whether the catalyst is itself is a heterogeneous, like oxides. Okay, many oxides, alkyl oxide, transition metal oxides, lead transition metal oxides, lanthanide oxides are also acts as a catalyst for various reactions. Okay, so we know that this heterogeneous catalyst is actually the surface chemistry. Okay, that we have already discussed. Okay, now I will discuss or show the basic difference in a very qualitative way in a pictorial diagram, so that you can easily understand what is the main difference. Fine. So, suppose I am doing some hydrogenation reactions or activating the HH as example in the last. Okay, here you will see. So, this is basically the activation of the dihydrogen or H2 normal H2 gas, which has a quite high bond dissociation energy of 412 kilojoule per mole. So, let us take a similar type of I will discuss in a very general way. Okay. So, this is suppose is let us say is a metallic one metals. Okay, and like that a metallic surface, it may be oxides, this may be elementary metals or alloys. Okay, anything, and here, and let us say that we are passing hydrogen. Okay, through this one. So, what will happen? Hydrogen is like this one. Okay. So, there will be now like that, it will be some kind of interaction, and this is called, I will discuss what kind of interaction it is, like okay, like that, and you will have okay. So, some kind of weak interaction, and this is called generally the interaction is van der Waals interaction in nature. Van der Waals type interaction is a very weak interaction at around 20 kilojoule per mole, and that is why it is reversible in nature. So, basically you can again H2 can be released in a very fast and easily. Okay. So, that is why it is a reversible in nature, and this is called the physisorption. This step is called the physisorption. Okay, this step. So, this is the physisorption, and this is called the physisorbed H2 on metal surface. Okay. And now, next you have, when these are in a close proximity to the metal center, that is the active center, then what will happen? There will be the chemical reactions as you have seen for the small molecules in a molecular chemistry, like oxidative addition, reductive elimination, that we have seen for the small molecule chemistry we have discussed. Okay, in case of homogeneous catalysis system. So, this is you can tell this step is the chemisorption, and this interaction is high, much higher than the physis option, and this is called the chemi-sorbed H2. Okay, and you will see here here first what is happening, this is a physis option is happening. Okay, and the reverse step you can tell this is called the desorption. Okay, the reverse step, this is very low in energy, that's why it's a reversible in nature, and then chemisorption, and then you see what is happening, MH bond is forming. Okay, as you have seen like for small molecular chemistry. Okay, I'll also give one example so that you can understand. Okay, now for the molecular chemistry what happens, I am taking again a very general structure. Okay, like L may be phosphine. Okay, if you want to be specific, L may be phosphine, M may be nickel 0. Okay, N may be nickel 0. Sorry, this one. Okay, fine. Now you will see that what will happen for if you, so this is a molecular chemistry, this is the surface chemistry and the first one, and this is molecular chemistry. Okay, now what will happen here, the let us say this, if it is nickel 0, that is the 16 electron system. Okay, so it can first undergo the coordination, so one L will come out and then it will be the classical eta 2 hydrogen. So it's basically the is first coordination here H. Okay, and this is basically eta 2 H2 complex. Okay, and if we calculate, it will be 18 electron if we consider M is nickel 0. Okay, now this is the now bond making step, that is the oxidative addition. We are all familiar what is oxidative addition. So here what will happen, okay, the geometry I am again writing very hypothetical, it may be square planar, it may be trigonal bipyramidal, depending on the ligand, depending on the metal center. So if one triphenyl phosphine goes away, then it will be square planar. Okay, so here you will see this is again the 18 electron system. Okay, and you will see that there is a formation of again MH bond. So in this case also MH, in this case also MH bond you will see. Okay, but the basic difference you will see here, that here it is the addition of hydrogen is a bimetallic in nature, and for molecular chemistry it is generally monometallic. Okay, but in some cases it may happens for as a bimetallic also, as example for dimeric compounds like a di-gold complexes, di-silver complex, or any other bimetallic complexes, that the oxidative addition in monometallic in bimetallic pathway also possible. But in the normal cases, in a molecular chemistry you will see that formation of the MH or new bond, it's in a monometallic nature, and for the heterogeneous system, that follows the surface chemistry, is then a bimetallic nature. Okay, like here you will see. So the basic difference you will see here in the surface chemistry, that is the heterogeneous system, physis option and then chemisorption, and in a molecular chemistry coordination, then oxidative addition, and then others like reductive eliminations, all those things. As example for heterogeneous happen like desorption, releasing the product. Okay. So, these are the steps in a very, I am discussing in a very simple way, so that it is understandable to everyone. I am not going in more detail about the kinetics. So, here I will now discuss about one example, okay, which is very much followed in industries, that is the Fischer-Tropsch synthesis or Fischer-Tropsch process. And what is that? Okay, this is very important, and it has you will understand why it is important. So, you can basically form the carbon monoxide and hydrogen, very simple substrates, okay, easily available, and what you will get? You will get the hydrocarbons, not actually the polymers, and non-toxic byproducts, the water. Okay. So, if you consider like balance CH2n and here NH2. Okay. And what is this? Is actually the catalytic iron. Okay. So, here what is two steps actually? What one is the reduction of carbon monoxide and then polymerization of reduced CO. Okay. And this is process called the Fischer-Tropsch process. This is very important. Okay. One of the heterogeneous reactions. Okay. And it is a $1 million market. And here you will see that this is what we are getting. We are getting basically from here hydrocarbons, which can be feedstock for many value added materials, as example for the fuels, the wax, the oils, etc. Okay. And this is called popularly, this reaction is gas to liquid. So, you will see here you are using two gases and you are getting a liquid, that is like low molecular weight alkanes. Okay. So, that is also popularly we call is gas to liquid. One of the very important heterogeneous industrial process for heterogeneous catalysts. Okay. Okay. So, this is a, you will see that heterogeneous polymerization supported catalyst in industries. Okay. And how does it happen, the reactions? Okay. Here this is very complex system. However, there are a lot of mechanisms are involved. However, I will just try to show you in the original mechanism proposed by the Fischer. Okay. And how does it happen? I will show you. Okay. So, you can consider that this is the iron surface. Okay. And here is carbon monoxide, fine, and here hydrogen, and this is weak interaction, the van der Waals interaction, as we have learned in our previous discussion. And as I told that heterogeneous catalysis mechanism is very complex to understand. So, see here and here formation. So this is, you can see van der Waals, this is the physics option, and then the chemistry option happens. Okay, and then in presence of H2, okay, so CH2 and this is CH, okay, and here CH3, okay, and then so these are, let us say, the iron active centers, okay. So this is CH3, this is okay, and this is CH2, okay, this is CH2, like that, okay, fine. Now here you will see it will continue, and you will see like CH2, CH2N, like CH3, okay, like H, like that. Now is interesting, okay, it can desorption, and desorption will produce the alkanes, and it can also undergo the beta H elimination, okay. So this hydrogen, okay, will be beta, and it can give the alpha olefin, okay, two as a minor products. So this is a very simplified Fischer mechanism. As I told that there are different mechanisms have been postulated by different groups. These are one of the examples, simple examples, okay. So you can see, understand that this is the physics-solved H2O carbon monoxide, this is the chemistry-solved, okay, carbon monoxide H2, and then this similar way the reaction, the polymerization reactions happens, and you will get the lower alkanes, but here you will not get the high molecular weight, you will get like a small molecular weight, the alkanes, okay, octane, heptane, nonane, like that, and also to some extent some alpha olefin also you will get, okay, fine. So now we understood that there, to make, it's an industrial process, to make is a practical implications, we have to transfer the homogeneous, very active homogeneous catalyst to most practical heterogeneous catalyst. So obviously there is a strong relation between lab and industry. So we have to make the active catalyst, we have to check it, we have to understand the mechanism, then we have to transfer to the lab, okay. So we very close relation between lab to industry, okay, academicians and industrialists, fine, and how we'll do it, okay, and that I'll discuss. And we now very familiar what is the advantage and disadvantage. I will not go in more detail, but for the metallocene based catalyst, some specific problems in homogeneous, like controlling polymer morphology with soluble catalysts, that is a very active catalyst. Sometimes it is difficult to control its reactivity. Large amounts of MAU needed, that is another very disadvantage. We have already discussed that sometimes the MAU has to be taken like 1000 times more, or sometimes like 10 to the power 3 or 10 to the 4 times more compared to the actual metallocene catalysts. So, co-initiator has to be taken in a large excess. Recovery of costly MO, the MAU and the metallocenes is very difficult because the process is not simple. Okay. So, obviously, to make the cost effective, economic and industrial acceptance, we have to transfer our homogeneous active metallocene catalysts to the heterogeneous catalyst system. Although there may be some sacrifice in the activity, in selectivity, but overall it will be more economic in nature. Okay. So, what we have to do it, okay, that is we will try to discuss now. Okay. What are the synthetic strategy? The synthetic strategy is or what are the basic issues we have to take care. Okay. That is we will try to discuss now here. But before that, I just want to mention about some few points of the Phillips type catalysts. Okay. And we already discussed what is the Phillips catalyst. This is also used as for ethylene polymerization, and this is basically the chromium based catalysts. Okay. Cr2O3 generally used in silica. Okay, in silica. Okay. Fine. So, what is that? This is, if you just consider this is a silica surface, okay, just a one unit of the silica. So, if you react with Cr2O3, you will get like this. Okay. And also, okay, so it is very complicated, very difficult to know exactly what actual system it is. Okay. And then this is oxide, this is oxide. Okay. Fine. So, this will be not there. Okay. So, here you will see that silica supported chromium catalyst, and these are highly used. So, so this is basically you see that Cr2O3 on silica or aluminosilicates sometimes. Okay, both can be done. And how it is prepared? It is prepared basically finely divided silica. Okay, and this is the aqueous solution, and we heat it around 5 degree centigrade to 18 degree centigrade. This is only for this one, but the temperature will depend, or the other condition will depend on your other the other catalysts, and you will get this one. As I told that the polymerization mechanism is different because is very complex. Both chromium 2 or chromium 3 can be involved. So, it is not very well understood what are the actually mechanism, but this I want to tell that this is how a polymerization catalyst, this is one of the oldest catalyst for ethylene polymerization, that is the Phillips catalyst, are converted to heterogeneous from homogeneous. So, very similar approach from the previous knowledge, we will try to see that how can be done for the metallocene based catalysts. Okay. So, let us come to our polymerization catalysts. Now, we all know that Ziegler-Natta, okay, is a heterogeneous catalyst, and it is used as supported, okay, as suspension or slurry in hydrocarbon liquids in polymerization reactor, and this is the gas phase process. So, the like ethylene gas is passed on this suspension and the polymerization happens. Okay. So, for the metallocene catalysts also, with the previous knowledge and the Ziegler-Natta, because Ziegler-Natta catalyst was very successful. So, metallocene, for metallocene also the similar approach can be done. This is called the drop in technology. The industry people took it like a drop in technology. Drop in technology means the same process we used to have a Ziegler-Natta, but we just vary the conditions. Okay. Same process. So, it is basically the same process or same fundamental aspects, but varying reaction conditions, because your main active catalyst is different. So, we have to vary some temperature, the concentration, the stoichiometry. Okay. So, and for that, okay, definitely for that heterogeneous metallocene catalysts is highly desired to make it a industrial process. Okay, because we just follow the same process as we are successful Ziegler-Natta catalyst in industrial process. So, it basically follow the concept of drop in technology with the metallocene catalyst. As Ziegler-Natta was the heterogeneous, so we will also try to transport the homogeneous metallocene to heterogeneous catalyst. Now, how it can be done? Okay, what can be done? Basically, the fixing metallocene okay on support. On support means either SiO2 or LO2O3 or maybe aluminosilicates, both. Okay, all these combinations can be done. Okay, and theoretically 3 ways can be done, because see, in our whole system what are there? We have the initiator, we have the co-initiator, and we have the support. Support means the silica or aluminosilicates. Okay. So, either you first react with support plus initiator, or what I am trying to say, that either this support with initiator, either support with co-initiator, or either you react with support with the initiator and co-initiator mixture. 3 ways possible, but the most successful are this one. What? That co-initiator is fixed first, okay, on silica. And how it can be done? It can be just reaction with MAU plus silica or trimethyl aluminum, okay, followed by the controlled amount of water and the silica. Okay. So, this is the most followed method by various industries. However, the other method, that is the co-initiator support plus initiator first, eventually it will give the same, or the support plus pre-mixed initiator plus co-initiator also can be done. Okay. So, here you see what is happening. So, this is basically your silica support, and we are now reacting with MAO, and you will see this is my MAO supported system. Okay. And now you are charging the main catalyst, and you will see that it will MAO Cl minus CpZr Me plus. So, it's basically you will see that now your main catalyst, that is this is the catalyst and this is basically co-catalyst. This will be electrostatically interacted and it will be on the support of the silica. So, these are the method generally we follow to make the homogeneous to heterogeneous. So, here you will see this is the strategy to prepare supported metallocene. Silica is treated with MAO followed by metallocene catalyst. Okay. That is the method we generally use. Okay. And experimentally it has been observed that this is the best one, okay, with a minimum leaching and other advantageous issues. Okay. So, some of the basic features you can tell that of these supported metallocene based catalysts, I just list down that has lower activity than homogeneous. That is obvious because you are converting to homogeneous to heterogeneous. So, you have to sacrifice some the activity, and due to this is due to the steric hindrance. If you see this one, so here you will see there is a silica means this is a polymeric network structure. So, you are putting lot of steric hindrance in the nearby the active catalyst surface, okay, and that is why you will say substrate cannot approach as easy as it is possible for the homogeneous system. Okay. So, this is sacrifice you have to do, but here the good thing is that here less MAO is required, okay, and this is because deactivation process is also slower due to the steric hindrance. Deactivation is also slower, okay, due to the steric hindrance, and polymer molecular weight and stereoselectivity are not affected significantly. So, that is good, okay, and most important issue is that this is reusable and cost effective. So, you can use the different batch of the polymerations, okay, in industries. Okay. So, these are the other possibility of the supported metallocene catalyst, that here we have, I have shown one strategy. Here you can see that you can directly attach the metallocene, those are more advanced, okay, although it is not still it is not well accepted in industries. We have to do some tuning and other method. We have to standardize the method. So, these are the very nice strategy. So, these aluminosilicates or silicates you can attach to metal center like that way, this one, or you can use the bridging methyl groups like this one, or you can, here you will see these silicates, okay, you can attach directly to the metal centers like that one. So, you can design our supported metallocene catalysts how, and we can develop a new strategies to make the supported metallocene based catalysts. Okay. So, these are some of the other strategies which are definitely, as I told, that is not still applied to the industrial synthesis, but maybe in future. Okay. So, however, some of the challenge, though it is a cost effective, but we have to sacrifice some of the points, and still there is a challenge to overcome in future, like prevent catalyst leaching, okay, the maintaining the single site characteristic of metallocene upon heterogenation, that is one for some cases, okay, or for some substrates this selectivity is a issue, because we are hindering. So we are basically that surface, the proximity of the metal center are hindered, and that's why if it may be difficult to some of the monomers to approach to the metal center, and that's why we have to sacrifice in issue of the activity and the selectivity. So there is some challenge, we have this, there is still scope to overcome, and the research is going on in industry and also in academics. Okay. So in conclusion, okay, today what we have learned a very important issues or aspects of the metallocene based catalyst, how to make the homogeneous metallocene, and same thing can be approached for the non metallocene compounds also. Homogeneous metallocene catalyst to heterogeneous catalytic system, advantage, synthetic strategy, and obviously some basic concept, okay, of the basic concept of heterogeneous catalyst, because this is important, otherwise knowledge will not be complete. Heterogeneous catalytic process, and thus we now understood how one catalyst can be transformed from laboratory to industry. So, we now know the journey pathway, the roadmap from lab to industry. Okay. This is very, very important, okay, to make the process viable and industrially useful. These are some of the references you can discuss. Those are, we have most of the our discussion we have taken from these references, except some are from some papers or reviews that already we have cited in the respective slides. So, with this, thank you, and in the next class we will be entering to a very interesting and and very important aspect, that is the depolymerization by the same catalysts, and then we will enter to the field of metal-carbene and complexes for the polymerization synthesis. Thank you very much, and see you in the next class.